We are on to Unit 7, Thermochemistry, and in Unit 7, we are covering energy. Thermo is heat, heat energy. And a part of that heat energy, the type of energy, is one other type of energy is called potential energy, and it's stored in the bonds. And so we're going to look at that stored energy being exchanged between the reactants and products, sometimes releasing energy or absorbing energy in the end. We have laws that embed this unit, which is the law of conservation of energy. And of course, just like the law of conservation of mass, it states that mass must be conserved. Law of conservation of energy states that energy must be conserved in a chemical reaction or different processes. Um, all This table is going to be a table of understanding the energy involved in certain types of bonds. So the potential energy. So this is all potential energy called average bond energy in each of these different types of bonds between elements. Sometimes you're talking about single bonds, other times you're talking about multiple bonds like double bonds and triple bonds, okay? Let's go ahead and look at our first problem. Our first problem says find the total change in enthalpy, which is potential energy, of the combustion reaction. So the first thing you want to do is balance this combustion reaction so you can see how many particles you have in this reaction. So let's start off with 2 carbons on the left side, right here, 2 carbons. I want 2 carbons on this side, so I'm going to put a coefficient of 2. 4 on the left side of hydrogens, I want 4, so I'm going to have to double that, and that gives me 2. And then let's say this is 1 here, and let's count our oxygens. There's 4 oxygens, 2 oxygens here on water, so that's a total of 6, which gives me a coefficient of 3. Why do we balance the equations? We balance it so that we can make sure the moles of each substance reacting overall is going to be conserved between the reactants and products. Now we're going to do part B, Roman numeral 2. Roman numeral 2 says that we want to draw the Lewis structure for each of these substances in the chemical reaction. And this is our steps to really calculating what is called total change in enthalpy. So we're going to draw it. The first substance if you can recall, is the following. And I'll rewrite the reaction so we can see what it is. C2H4, and I believe there is a coefficient of 1. Reacting with, there was 3 oxygens. And then I'm just going to continue on, and there was carbon dioxide and water. And let's put the coefficients in. They were 2 and 2. Okay, so let's go ahead and draw the Lewis structure for each of these. What does that mean? I'll draw the Lewis structure for C2H4. I'll also draw the Lewis structure for O2, but 3 of them. I'm going to make sure I stoichiometrically represent how many particles there are. So the first substance is C2H4. To draw this substance is to follow your rules for Lewis structure. So there's a little refresher today. We're going to refresh how to draw Lewis structures. So the 2 carbons are going to be your central atoms. And since there's 4 hydrogens, I'm going to split 2 of them on this end here, and then the other 2 on the opposite. Okay, and then 1 dot for 1 valence electron for hydrogen. So I'm going to bond those, and of course I'm going to bond the 2 carbons together, leaving me with a double bond right here. So that is C2H4. Now I'm going to do oxygen. Oxygen has 6 valence electrons, if you recall. I'm going to draw all my unpaired electrons next to each other so that they can be bonded, possibly double bonded. So it looks like there is going to be a double bond, and the double bond is going to be between the 2 oxygens. There's 3 of them, so once I have my first structure, it's as simple as just drawing the structure with some shortcuts as far as lone pairs. So I'm going to draw these 3 times because there's 3 moles of oxygen. Likewise, I'm going to now move on to carbon dioxide. And once again, I'm going to draw carbon, draw it slowly first, and then I'm going to work my way to drawing 2 of them ultimately because there's 2 moles. Okay, do my single bonds first. I see that it looks like I'm probably going to need to double it up. And then I'm going to erase I'm going to pair up my bottom pairing so that I can do another double bond if that's needed. So it looks like, here's the pair, another double bond. So it looks like carbon dioxide has a double bond with the oxygen and 2 lone pairs. The carbon has a double bond with the oxygen and 2 lone pairs. Water seems to be I think a lot of you have a pretty strong, quick hand at drawing water. So this is your 2 water molecules. All right, the next step that we need to do is sum up the reactants and then sum up the products separately. And why we do that is to subtract to get what is called the enthalpy, the change in enthalpy, which is delta H. So I'm going to sum up the reactants. Now, to sum up the reactants, I have to look at my potential energy chart, which is the previous page. It has a chart of all the average bond energy. So these are all the average bond energies that I retrieved from the previous chart with the average bond energies. A double bonded carbon-carbon is 614 kilojoules per mole, and then a carbon-hydrogen is 413. A double bonded oxygen-oxygen bond is 495. 799 for carbon-oxygen double bond, as well as a single bond oxygen-hydrogen is 463. Now, I have to add and tally up, I have to do a multiplier of this value times 3 because there's 3 of them. So you do have to do your multipliers depending on how many you have of each of the bonds, okay? So for CH bond, I have 4 of them, so I'm going to multiply that by 4. So let's set that up. I'm going to do reactants first, and then I'll do products afterwards, okay? Reactants, I have 614. I'm going to add 413, and I'm going to multiply that by, and I'll put my multiplier in a different color, times that by 4. Because there's 4 of them. 1, 2, 3, 4. Them being 4 carbon hydrogens, so there's 4. And then I'm going to continue on adding the 495 times it by 3 in the end. And so I'm going to times that by put the 3 there because there's 3. 1, 2, 3. So now I tally up my value and get my total sum of the enthalpy, the bond energy of my reactants. Now I begin my products. 799 is my double bond between carbon-oxygen, and there's 4 of them. Can you all see the 4? Make sure you're looking at your structure. This is why you draw the Lewis structure, so that you can see 1, 2, 3, 4 total. And you draw however many moles of them so that you can actually see them, count them. And then you go to the products, and the products, there is 463 times that by 4 as well. And then you sum them up. So pause and make sure you sum. These are the values that I got after I summed up all the reactants. This is my final value, and then I summed up all my products. Now, to find the enthalpy, the equation is simple. You just take the bond energy broken, which is in the reactants. You had to break all these bonds up to then make these bonds in the products. So that's why you're seeing a releasing of energy when you're making bonds versus breaking them. So the edit here should be made. So bonds made in the products. So ultimately, when you break bonds, it requires energy. So it's a positive value right here. Whereas when bonds, you are releasing energy. So that's why it's a negative value in front here. It's subtracted. Okay, so let's go ahead and put our values together. Enthalpy of a reaction is the bonds broken in the reactants, which was 3,751, minus the bonds made in the reaction. Well, formed and made is the same thing, so I'm going to put the word formed also. Same thing. Okay. Now, as a result of subtracting those two values, I should get a negative value because the average bond energy of the products is greater than the average bond energy of the reactants. So I should see heat or energy being released, and that negative shows that 1,297 kilojoules per mole of energy was released. So this negative indicates a releasing of heat. All right, next up, the change in enthalpy is the total change in delta H is the total change in enthalpy, or overall heat content in the reaction. Graphically, it can be represented in what is called an energy diagram. Thus, you see the potential energy is the y-axis. X-axis is basically progress of reaction. It could also be time. Which graph does the above combustion reaction represent? Well, since you're releasing energy, you know that the potential energy of the products is lower than the potential energy of the reactants. So this leads to a negative delta H, which you see right here, negative delta H, and thus this reaction, the exothermic reaction is what a combustion reaction represents. So exothermic in the end. And once again, read this part. A negative delta H means there are more energy released when the reactants become products in the chemical reaction, as opposed to a delta H of positive means there's more energy absorbed for the reactants to become the products. So that's why the products, if your reactants are absorbing more energy, the ending products will have greater potential energy than the reactants. Normally, most reactions, it's much more favorable to be exothermic in the end because you're releasing energy rather than requiring more energy than what you started with. Model to show how heat is exchanged between the systems. So if your reaction is occurring in here, and I'll go ahead and write the reaction, C2H4 reacting with 3 moles of oxygen to form 2 moles of carbon dioxide and 2 moles of water. If this is all happening inside this system right here, and we know that heat is released out of this reaction, so what we're going to do is we're going to take this reaction and say that delta H is going to come out to the surrounding. So if you have your hand in here, so say I'm going to touch this. This is your hand. I'm going to touch this. What I would feel is it's going to feel hot. It's going to feel hot from the heat that's released. So it's going to feel hot from the heat that's released from the system. By the system. Which is where the reaction takes place. Okay. Moving on to energy diagram. We've already had some exposure with energy diagram earlier. This is just a formal description of it. So in an energy diagram, you have reactants, the potential energy of the reactants, and then of course compared to the potential energy of the products. There's something called the activated complex, which is which is a transition state between the reactants becoming products. And the activated complex is very unstable. And what makes it unstable is because it has some bonds that's why it has a high potential energy, because it has some extra bonds in there that are not quite structurally stable and sound for the substance. So the activated complex is that transition between the reactants becoming products. Activation energy is basically this hill to climb. It's basically the energy from the reactants to becoming the activated complex. And then the enthalpy, which is the change in your potential energy between the reactants and products, is this distance right here. And we can actually see it graphically in this energy diagram. Now, this is an exothermic energy diagram where the potential energy of the products is lower than the potential energy of the reactants. In an endothermic reaction, the product's potential energy is greater than the reactant's potential energy, and thus the delta H is going to be positive in the end, which means endothermic. Negative exothermic. Enthalpy, negative enthalpy change is exothermic. All right, let's take a little time and practice this. If you look, E means energy, in this case potential energy, and R represents the reactants. TS represents the transition state, which is, by the way, another way of calling the activated complex. So it's up here. And then P represents products. So it's asking for the potential energy value of the reactants. And so the reactants right here is AB, and the energy is 40. So I am going to put 40 kilojoules. The activated complex is up here, which is a transition state, so the potential energy is 100. The products is right here, and so the activation energy is 20 kilojoules. Now calculate the activation energy for the forward reaction. So let me describe what it means by forward reaction. So when I go from reactants to products, I'm going in the forward direction here. But then when I reverse it, that means I'm going from the products becomes reactants, and then the reactants becomes products. So it's going this way, right here, this way. So forward and reverse goes the opposite way along this diagram, the energy diagram. So I'm calculating the activation energy for the forward, and it's always the hill to climb from the beginning, which is the reactants, to the activated complex. Okay, so it looks like the activation energy, the amount of energy, is the difference between 100 and 40, which is 60. So the answer is 60 kilojoules. Now we go to the activation energy of the reverse. So in the reverse direction, you're going from here up to the top activated complex. So now your reactants is this, C and D, and it's becoming the activated complex. So what is the difference in the potential energy? So you're going from 20 to 100, which means it's 80 kilojoules. Now, which one requires more energy? The forward direction as far as the activation energy, or the reverse? And you're right to say the reverse requires more energy. So what's more likely to happen is the forward direction reaction. So the reaction probably is more likely to go in the forward direction than the reverse direction. All right, next up, we're calculating the enthalpy for the forward reaction. So the enthalpy is always the products minus the reactants. So the value for the enthalpy of the products is 20. So I'm going to take 20 minus the reactants, which is 40. 20 minus 40 gives you negative 20 kilojoules. So this is exothermic. We know that a reaction that leads to a negative enthalpy is exothermic. Now we go in the reverse direction. In the reverse direction, now our reactants is right here, products is right here. So once again, enthalpy is always products minus reactants. So we're going to take the 40, which is AB's products, minus the reactants, which is 20. And you'll notice that the sign reverses when it becomes the opposite reverse direction. So whereas the forward direction, the enthalpy was negative 20, the reverse direction, the enthalpy is going to be the opposite, which is positive 20. And that, by the way, is opposite also in terms of how we label the type of reaction, and that is endothermic. Show the effect of a catalyst. Okay, so what a catalyst does is a catalyst speeds up a reaction. That's the definition of what a catalyst is. Whether in biology we call that an enzyme, a catalyst is any kind of compound that speeds up the chemical reaction. Okay, so how do we speed this chemical reaction up? Well, to speed this up, what we do is we lower the activation energy. So this is what a catalyst does. It lowers the activation energy. And I'm going to label it catalyst added right here. And in lowering the activation energy, the hill to climb is less, and so it's faster to get to the products. And that's exactly what you're seeing here. Is the hill to climb is lower, thus the activation energy is less, allowing us to get to the products quicker. And that's how we speed up the reaction. This question of which burns longer, a piece of coal or a piece of wood, both the same size and the same mass, and please explain. Well, if you think of coal and wood, what do we use for our energy source? And our energy source used to be wood, but now it's coal. And that coal obviously probably is bonded in a certain way that makes coal a more efficient energy source. And that is probably because it's stronger, more bonds, or whatnot. So it has to do with the bond type that would make coal burn longer, and the bond strength as well as the bond number of bonds that are in coal versus wood. So definitely coal would burn longer. Okay, what is the difference between heat and temperature? So here's the difference. Heat is a process. It's a process of flowing energy, kinetic energy from a warm object to a cooler object, while temperature is the average kinetic energy. So let me describe temperature and heat flow in terms of the motion of particles that you see right here. So if you look at this particle or this scenario, this is this is a conductive layer. So I am going to note that there's conductivity here. It's a conductive layer. What I'm doing is I'm heating one side, and notice the same number of particles are located on both sides, and so these particles are going to move faster. And as it moves faster, that energy is going to hit along this conductive layer, which then will transfer energy over to this side. So heat is going to flow from this side from the right side to the left side. And that's what you're seeing as you describe what's happening to the particles. Once again, this Bunsen burner is going to cause these particles to move faster with more kinetic energy. That energy, when it hits this conductive layer, is going to transfer over to this side. So that side is going to absorb that energy, and these particles are going to move faster, thus increasing its heat, its temperature on this side. So now notice also that a high temperature side, like this side on the right side, is going to go to a low temperature, and I'll make it in blue so that we can really obviously see that. So a low temperature, which is this side. Just make sure you take the time to write down that description of how the heat is flowing between the two sides of this system here. All right, what's heat? Heat is the energy in the process of flowing from a warmer object to a cooler, just like you see here. This is what the heat symbol is. And so we use the symbol of a triangle to represent what heat is. And of course, we show arrows for the direction of where heat is flowing in the end. All right. How do we measure heat? We measure it through a unit called calorie. Calorie is the energy, specifically heat energy, required to raise the temperature of 1 gram of pure water by 1 degree Celsius. What other substances are used to measure heat? Or sorry, what other units are used to measure heat? Well, there's other units like joules, kilojoules, kilocal, which is actually one big C cal. They're equivalent. And this one big C cal is actually nutritional. This is your nutritional calories. We're going to measure heat. But before we do that, let's make sure we can convert between heat units, these units like calories and joules. Here are all our conversions. To get from small c calorie to kilojoules or to joules, you see this equivalent statement right here. 1 cal equals 4.184 joules. Big kilocal is really 1,000 small c calories, and of course we know a kilocal is equivalent to a big C calorie. Kilojoules and joules are related through 1,000. 1,000 kilojoules equals 1 joules equals 1 kilojoule. So we're going to convert. We're going to convert from calories to joules in this first scenario, and then nutritional calories to joules, and then kilocal to cal. Easy conversions. And in any conversion, we're using dimensional analysis. So I'm going to start with my given, which is 25.0 calories, and I'm going to set up my units to cross cancel and the units that I want in the end. And I know the converter that I'm using is this first converter. I'm going to put 4.184 into my joules and then 1 cal. And then I'm going to cross cancel my units. I should get 105 joules as my answer. I do the same for all the other ones. I'm just going to go through the calculation using dimensional analysis. So this next one, I'm going to need to change this to small c calories. So what's the relationship between small c calorie and big C calorie? And that's 1,000 small c calories is 1 big C calorie. And once again, I want to get rid of my small c calorie and convert it to joules. I'm going to use that same converter as the previous problem. There's 4.184 joules in 1 calorie, and my answer in the end is 46. Pause and make sure you work through the next problem. When you unpause, you'll see the answer. Here is the answer. Go ahead and work through the next example, which is you're converting from kilojoules to small c calories. There's the answer. Go ahead and check your work against the answer. I should make a habit of cross-canceling my units. So I do want to talk about this question. Is this reaction endothermic or exothermic? And there are words that really suggest whether this reaction is endothermic or exo. If I hear the word absorbed, that means it's endothermic. Take in, absorb. Exothermic means release of energy. So those are your keywords that help you to know whether the reaction is endothermic or exo. And so since I see the word absorbed here, that means it's endothermic. All right, next up, we're going to talk about specific heat. By the way, we're using all of these ideas and putting it into eventually calculating it using this equation right here down below. But specific heat. Specific heat is denoted by the symbol C. And specific heat of different substances are listed right here. It's usually a constant value for different substance. It's truly the amount of energy that can be absorbed by that substance before 1 degree or 1 gram of that substance changes by 1 degree Celsius. Truly, by the definition, you can, or the units can be, from the units, you can actually define what specific heat is. Again, it's the amount of heat required to raise the temperature of 1 gram of one substance by 1 degree Celsius. Notice the 1 degree Celsius down here. I know there's no one, but anytime we see per something, it means one for each of these, right? All right, one of the reasons beachfront property is so expensive is due to the fact that there's stable ambient temperatures along the coast. Explain why temperatures do not fluctuate significantly throughout the day using the specific heat of water. So water has a high specific heat compared to these other substances that you see. And that's because water absorbs a lot of heat. So that's why this value is high before 1 gram of that substance changes by 1 degree Celsius. So that high specific heat is acting to absorb the heat during the day time, and then it releases the heat during the nighttime when it gets cooler in the air. So the water molecules in the air is actually doing the absorbing of the heat during the daytime when it's hot. So the heat from the air goes to the water molecules, which is cooler. But then at nighttime, when the air is cooler, that heat that's stored in that water is going to release to the air. All right, there are two equations you're going to be learning in this unit, and that's what makes this unit pretty doable and straightforward. It's Q equals MCAT, which is when you have no phase change, and then there's also Q equals it's the phase change equation, which is Q equals M times change in enthalpy, which is delta H. That's the other equation. Let's work with Q equals MCAT first. These are all the variables for um, what each of these variables represent. Q represents heat, M represents mass, C represents exactly what we saw up here, which is specific heat capacity, and then these are the units for possible units for specific heat capacity, and then delta T is the change in temperature between the final and the initial, and it's in temperature or degrees Celsius. Oftentimes your constant tells us what the temperature units are, so this must be in degrees Celsius. That's how I know. Let's look at the problems so that we can use the equation. So now what we're looking at is no phase change. What that means is we're just heating an object up. That's all. There's no melting, boiling, no phase change whatsoever. Whereas the next set of problems with the next equation is going to involve phase changes. Once again, what I like to do is look at the problem and just identify variables. And so this is my change in temperature between what's happening between the object when it's cooler and then when it's warmer. So notice how it got warmer because you're adding heat to raise the temperature of a certain mass of this object. So the first thing I want to do is now to calculate what I want. What do I want? It's the Q, the energy. And it's in kilojoules, so I really want to note the units, okay? So I'm going to use Q equals MCAT. The M is the mass. The C, the specific heat capacity, is this 0.900 of aluminum. By the way, it tells you right here that this is the specific heat capacity of aluminum, and that's the value. And then change in temperature, we're seeing a change of 13.0 degrees Celsius to 3.0 degrees Celsius, which is about 10 degrees Celsius once you calculate that, right? Oops, I forgot my sig figs. I really want to stress my sig figs, which is 0.0 degrees Celsius. So multiplying everything out, you will then, unit-wise, get a final answer and value. And the Q ends up being It has to be in joules, so 450 joules. So, but then, oh, sorry, check your units out and the cancellation. Notice it's in joules in the end. I want it in kilojoules, so I'm going to have to do a quick little side conversion between joules and kilojoules. And I know that in 1 kilojoule, there's 1,000 joules. Now you can move the decimal places also. You can sit there and go, okay, here's the decimal place, move it over 3 spaces to the left to get to kilojoules. That's the fast, quick way to do it if you know your dimension or your metric conversion. So this is 0.450 kilojoules in the end. Here's your answer. So number 2, an unknown substance with a mass of 10.0 grams is cooled, and here's your temperature change here. And of course, this amount of heat, Q, is released. Is this reaction endothermic or exothermic? And again, there's the word release, and that's the energy that's released, so I would say exothermic. Again, there's always some clues to tell us whether it's endothermic or exothermic by the terms that are in that. We're asked to find the specific heat capacity of the substance, identify the substance using the table from above, which is the previous page. That would mean you would need to go to the previous page for that table when you're ready to after you've calculated the specific heat capacity. So specific heat capacity is actually a way for us to be able to identify a substance. We're going to do MCAT. Heat would be 1200 joules. I'm going to convert it to joules very quickly. The mass is 10 grams. The specific heat capacity of this unknown substance, and I'll just call it an unknown substance. UNK stands for unknown. And then change in temperature, we're looking at 100 degrees change in temperature. And that's what we're going to do. Calculate and solve for specific heat capacity of our unknown substance. And it turns out to be 1 point, and I'll have to calculate that to be precise. 4.2, and yeah, that's all the in joules. Joules per gram times degrees Celsius. So who is this substance? It looks like it's, looking at that table from the previous page, it's liquid water. Let's go pause and work through number 3. You see me do 2 problems. Go ahead and work through number 3. And you unpause, you'll see the answer in the end. So I chose actually for this particular problem to keep it in calories, and so I used the specific capacity of water in calories right here, which was converted. And so yeah, I chose also to solve for delta T, which is the change in temperature. So this is your change in temperature of 6 degrees. And if you're cooling it, that means the temperature final is going to be lower than the temperature initial by 6 degrees. So it is 54 degrees Celsius. Let's talk about the heating cooling curve. Since we are calculating heat, it makes sense to be looking at this heating cooling curve. There's a couple of things that you want to look at, and I'll walk you through it. Every substance, just like every substance has a phase diagram, every substance has a heating curve and cooling curve. It reflects very much the phase diagram. So to start, at low temperatures, so T is the y-axis. At low temperatures, you're seeing a particle be in the state of a solid. As you heat that particle up, it goes through a phase change, and this is a phase change right here. So what's happening during a phase change is temperature stays constant. So temperature stays constant, and that's how you know you're boiling, freezing, melting. You're going through a phase change. And then, so there's an equilibrium between the solid and the liquid phase. And then you move forward into all the solid becoming a liquid. So now you have all liquid. It's warming up until you break through and there's an equilibrium between the liquid and gas. So this is another phase change where temperature stays constant, as you see here through D and E. Then you go into overcoming all those intermolecular forces that are holding the particles close together in the liquid phase to become the gas. And so now you're just a gas, pure gas, warming up through here. Changes in temperature are always changes in kinetic energy. So you're increasing kinetic energy here. But then now what you're going through as you're going through this phase change is you're increasing in potential energy. So that kinetic energy is transferred to potential energy, stored energy, and then you increase in kinetic energy. Once again, anytime you see temperature, temperature is defined as the average kinetic energy. You're seeing kinetic energy changing here, increasing specifically because it's going up. Temperature is also increasing here, and of course, potential energy is increasing. Now, why is this potential energy during a phase change? Well, during a phase change, what you're trying to do is break apart the solid so it can become the liquid. So you're really releasing energy as you're breaking these bonds. So the potential energy is increasing due to that bond breaking, bond making situation. But specifically, you're breaking those intermolecular forces going through this phase change. All right, let's go to what you're seeing here. Which segment, A through F, shows increasing kinetic energy? So you're looking at anything where you're seeing a segment increasing temperature. And so it's AB, CD, and EF. Which segment, A through F, involves changes in potential energy, which is phase changes. So it's BC, DE. Those are the only two. What is happening? Fill out the chart, and it tells you, asks you what is happening as you go through each of these. Read it and make sure you understand what's going on. During AB, all you're seeing is a solid B there, and so really there's no changes in potential energy whatsoever. And remember that potential energy is, in fact, enthalpy, change in enthalpy. So they're related. They're directly related to one another. They're actually equivalent. KE is also directly related. Change in kinetic energy is change in temperature, so they're also directly connected. As a solid, the particles are really just warming up. That's all you're doing. There's no bond breaking as a solid, pure solid. The opposite of the direction is also true. There's no bond breaking, and so you can't speak of endothermic or exothermic. All you're doing really is the particles are vibrating more or less depending on if you're going from A to B versus B to A, back to A. So particles are getting more energetic and moving, vibrating more in place. Now, when you get to phase change, what you're seeing is really an endothermic or exothermic process with the enthalpy changing. So if you're going from a solid to a liquid, yes, it's endothermic. If you're going from a liquid back to a solid, it's exothermic. So in one direction, it's endothermic. In the other direction, it's exothermic. What is happening, by the way, there's no change in kinetic energy during that time, so there's no temperature change. What's happening is you're breaking up bonds. You're breaking up the attractive forces, so the distance between the particles increases, and thus you're changing the potential energy, not the kinetic energy. Here you're making bonds, and so by breaking, it's endothermic, and so you see a higher changes in the bonds, which is changes in the potential energy. Moving down, liquid phase, yes, the particles are sliding past each other more or less depending on which direction, going from C to D versus D to C. And once again, all you're doing is changing the kinetic energy, which is the change in temperature. There's no changes in bonds. When you go through a phase change like this, D and E versus ED, you are going and breaking bonds versus making bonds in the other opposite direction. Lastly, gas particles are moving freely, and all you're doing once again is heating it up, moving the particles more, and thus there's more kinetic energy. So that's why they're moving more freely. All right, let's fill this out and make sure you understand what's happening along each of the segments. Identify where the melting starts and stops. All right, melting starts if you go back to your heat curve. Make sure you're going back to your heat curve. Melting begins at B and it ends at C. Where's freezing? Freezing begins at C and ends at B, so it's the reverse. Where does vaporization start? It starts at D. And where does condensation end? D as well. So it's vaporization begins at D, and then if you go the opposite way, condensation ends at D. Which segment shows the greatest change in heat? And so I'm looking at the x-axis, which means I'm looking for the largest stretch. And it looks like, it's hard to say, but really it should show DE showing the greatest change in heat, honestly. So the graph needs a little bit of editing, and I will edit for you to see that. The greatest change in temperature is going to be C and D. So CD around that, or you can say DC. Likewise, you can put ED here. Now we get into phase changes. So heat calculations with phase changes. And with any phase change, as we've seen here, we're breaking bonds or making bonds. Breaking or making bonds. And so that means it involves enthalpy, change in enthalpy, like you see here. There are two possible equations. You can work in mass or moles. It really depends on the enthalpy that's given to you. If it's per mole versus per gram, that will determine whether you're going to use moles versus mass. So you have to be vigilant of the units for enthalpy to figure out what equation to use. Once again, Q is heat, all these units for heat, mass versus moles. And so you can see it oftentimes here in mass here, joules per gram, as far as the enthalpy of fusion. What is fusion? Fusion is when you're melting. So we use the word fusion as the melting point or / freezing. So please understand that this is the value you'll use in calories or joules depending on whether you're melting or freezing. Enthalpy of vaporization. Vaporization is also called latent heat of vaporization. It's a really big value compared to fusion, but it's also in calories and joules per gram in this case. But again, be vigilant. Sometimes it's given in per moles. What keywords are you looking for when it comes to enthalpy of vaporization, condensing, or boiling or vaporizing? So all these words that you're seeing, keywords, you're looking for those words. Let's work through one of these problems. I have here the heat curve so that we can use it to know where we're at and what equation to use. Just giving you a brief little overview. Whenever we're using warming, you're using Q equals MCAT. So anytime you see a change in T, that makes sense that you're using Q equals MCAT, because Q equals MCAT involves delta T. So notice the delta T. That is changes in temperature. But then now when you go through a phase change, you notice that the temperature doesn't change. So if we were to put no change in temperature, you'd be left with no heat involved. But we know that phase changes involve heat. If you're melting, it involves heat. If you're boiling, it involves heat. So we rely on another equation to use to be able to calculate during that phase change, and that's Q equals M times delta H. So you're using bond energy because you're breaking up bonds during that time. Or enthalpy, which is where you're breaking bonds. and that's why you're seeing enthalpy be involved in that. Okay, with that brief little overview, let's go ahead and see which equation to use given the problem that we read. It says calculate the amount of heat in joules required to freeze 100 grams of water. So I'm hoping this is water's heat curve, and I know it's water's heat curve because of these phase changes. We know water freezes or melts at 0 degrees Celsius, and then it boils at 100 or condenses at 100 degrees Celsius. So we certainly know this is water's heat curve from that, both those phase changes and the temperature of those phase changes. So what segment are we looking at? Well, class, if you look at it very carefully, you're freezing. So we know this is where freezing occurs. And so the equation is going to be an enthalpy equation. And the correct equation is going to be Q equals, the precisely correct equation is going to be Q equals enthalpy of fusion here, change in enthalpy of fusion. The segment we're looking at is, so since we're freezing it, we're going from C to B, rather than melting, which is B to C. Now, let's go ahead and calculate. So we know what equation to use. We're going to use the mass, which is 100 grams given to us. And then the enthalpy of fusion for water is given to us earlier in the table. There were two values. One was 334 joules per gram or 80. And I want it in joules, so I'm going to pick the 334 joules per gram. Notice the grams cancel out, leaving us with joules. So this is 33,400 joules. Moving on to the next. Calculate the amount of heat in calories to vaporize 120 grams of liquid water. Once again, this must be water's heat curve, and so we're vaporizing, which is right here during this phase change. I'm going to say we're going to use Q equals M times delta H of vaporization. And so the segment we're looking at is we're going from D to E. It's good to know what segment, honestly, because there are problems that get a little bit more complex. So it's important to look at what segment you're looking at. So we're going to use Q equals mass, which is 120 grams, times the enthalpy of vaporization. And this time I'm going to pick the calorie unit one, constant, because I want it in calories. So my answer in the end is 64,800 calories when I calculate it. Last problem, go ahead and pause and make sure you work through this one. When you unpause, you'll see the answer. I'm always vigilant of my units, and so in this problem, it's asking for molar heat of fusion, which is your change in enthalpy, and it's in kilojoules per mole. So I'm going to use N times the enthalpy equals Q. And I'm going to rearrange this equation so that I can solve for molar heat of fusion, which is your change in enthalpy. That's another way of saying change in enthalpy of fusion. And so I'm going to divide both sides by N, which gives me Q divided by N. So heat per mole. And heat is in kilojoules, so I am going to set myself once again so I can get kilojoules per mole. Mole on the bottom, kilojoules on top, and when I ratio that, I get my 6.02 kilojoules per mole. Heat flow. Let's go ahead and flow heat between objects. And so heat, once again, is Q, and when we flow heat, the heat that's lost is going to give you a negative here. Heat that's gained is going to be a positive by another object. You oftentimes flow heat from a warmer object, because warmer goes to cooler object. Heat always flows that way. Therefore, the warmer object will lose its heat while the cooler object will gain heat. And gaining means positive, losing means negative. And that's why you see this negative sign right here and positive sign right here. By the way, these negative signs and positive signs will be very important for the delta T in the end, to ensure that ultimately delta T is going to be positive or like an absolute value for both of these. So it's never going to give you a negative value, which then wouldn't lead to any possible negative mass or specific heat capacity value. Mass or specific heat capacity. All right, let's go ahead and work through this problem. Okay, so I'm looking at two objects in a problem like this where there's heat transfer, silver and water. I'm transferring heat from the silver, which is really warm, 125 degrees, 0.00 degrees Celsius, and it's dropped into a room temperature water, or close to room temperature water, which is 20.00 degrees Celsius. Eventually, the heat's going to transfer from the silver to the water such that the final equilibrium temperature is 23.77. So the water's temperature is going to be heated up from 20 to 23.77 degrees Celsius. It's asking what is the mass of the silver. So this is a heat flow problem. I know it. I see two objects. I see heat flowing between two objects. And the two objects specifically is silver and water. So this is how I map out what I'm looking at. I'm trying to find the mass of silver. So silver is Ag, okay? Here is the initial temperature of silver. Here is the final mass. By the way, I know it's mass because I know density of water. Density of water is 1 gram per milliliter. If I have 30 milliliters, I have 30 grams. So I know that's where I'm going with that. T of initial of water, T final of water. It's also the T final of also the, so both the water and the silver. So silver and water are going to get to the same temperature in equilibrium with one another. So first thing you do is write a heat flow statement. So the heat lost by silver is going to be the heat gain by water. And as simple as this equation is, it helps you to know where to go with this problem. So you're going to insert heat, and heat is MCAT of silver, and then you're also going to insert heat, which is MCAT of water. So everything is going to be separated into this, revolving around this heat flow statement. So I'm going to put a minus. Mass of silver is unknown to us. We're going to make that as our unknown variable. I'm doing MCAT, by the way. So what is the silver's specific heat capacity? It's 0.235. So I'm going to substitute that into the specific heat capacity of silver. Then I'm going to do change in temperature. Now, the change in temperature is going to be T final, which is right here, minus the T initial. You'll notice that when you subtract these two, you'll get a negative value. That negative is going to be offset by this negative to make it a positive in the end. But I'm going to write that in so I can see that happening. So 27.33 minus 125.00. So that is, by the way, the heat of silver. And once again, these two values subtracted is going to give you a negative value. And the negative value that you're going to get for that difference is, I'm calculating my calculator, negative 101.23. That will be the difference. And so that negative is going to offset this negative by making it all positive in the end, okay? So that's the purpose of that negative, is to ensure that our change in temperature, though it's cooling down, is going to be a positive value difference in the end. So now let's finish this up and do water. So I'm going to do water side. The mass of water we said was 30 grams. Specific heat capacity of water is 4.184 joules per gram times degrees Celsius. The change in temperature of water is 23.77 minus 20.00 degrees Celsius. And then, so you set those two equal. Now you have one variable to solve as you're equating these two heat that is exchanged between objects. And then you solve for the mass of silver. And the mass of silver ends up being 19.89 grams. Let's go to the next problem. I would like for you to try setting this up yourself, but really essential, I'm just going to remind you, heat flow statement starts and begins the problem and helps us to end the problem. So please make sure you do that as you're going through this, okay? Once you unpause, I will have it all set up also for you and finished. I'm going to do the math to help you to see how to solve for TF in the end. So here's your TF and here's your TF. They're the same TF, by the way, so this is the same exact variable that you're going to solve for. I'm going to bring this negative in and bring it into this term here. When I do that, I flip-flop everything. What do I mean by flip-flop everything? This now becomes 131 minus TF instead. So that means this negative goes away, okay? As a result, I can then multiply these two values first and then distribute into this term here. And in doing so, I am going to get 25 times 0.129 times 131. So I'm going to get 422.475. And the term that I'm going to get after that is minus 3.225 TF. This is helping you out how to solve as far as the mathematics of how to solve this. Now I go to the other side. So I'm taking 80 times it by 4.184. And that certainly gives me 334.72 TF. So these are the same two TFs, okay, class? You really want to make sure you track your math. And so now I'm going to multiply that times 22.2, and that will give me my constant, which is 7,430.784. Now, math has always said to me, or solving an equation with algebra in algebra always says isolate the variable, bring all the variables onto one side, and then bring all the constants onto the other side. So here's the constant. I'm actually going to bring this constant over to this side instead. So that means I'm going to add, mathematically, I usually wouldn't show all these steps, but math these days, we want to make sure we show your steps so you can understand what you're doing. So I'm going to add 7,430.784 on both sides. And then I'm also going to add 3.225 TF on both sides as well. This zeroes this out, this zeroes this out, and so I'm left with adding all my values together. So 334.72 plus 3.225 gives us 337.945 TF equals, and so adding these two numbers, 422.475 plus 7,430.784 gives us 7,853.259. Divide both sides by 337.945, and you will get your answer in the end. Please make sure you work through that last step of calculation. So your TF isolated by itself is going to be 23.24 degrees Celsius. And try to make sense of the answer also. The temperature of the final temperature should be higher than the initial temperature of water because the hot gold is going to transfer the heat to the water. And so that's why the temperature is higher in the end of the final. The final temperature is higher. Now, you're having mixed problems where you're dealing with phase change and no phase change. So really, it's a series of segments that you're calculating the heat for as you're going through the heat curve. So let's look at this first problem. Calculate the amount of heat required to heat 100 grams of ice at negative 10 degrees Celsius. So if I try to find negative 10 degrees Celsius on the temperature scale, it's about right here estimated. And right here being negative 10 degrees is where X marks the spot for the starting point. Now I'm going to try to get to steam at 105. 105 is right here. And I'm going to draw a dotted line so I can see that it is 105 degrees Celsius. So I'm going through a series of segments here. I'm actually going to just heat up the ice first, and then I'm going to go through melting. Then I'm going to heat up the liquid quite extensively, and then I'm going to boil, and then I'm going to heat up the gas. So there's 1, 2, 3, 4, 5 segments that I am going to have to calculate my heat for. And those segments are segment AB going into, oops, wrong spot for that. AB going into BC, and then that will go into CD, DE, and EF. So all of those segments, and so there are several equations we're going to be looking at, and that would be Q equals MCAT for sure. But realize that the specific heat capacity will change depending on if it's ice, liquid water, or steam. So we have to look up the specific heat table for that. And then we're also going to use Q equals mass times delta H of vaporization slash fusion. So we're actually going to go through 2 phase changes, thus we're going to need to calculate each of those. So I'm going to organize it by segment. I'm going to start off with saying segment AB. Segment AB is along this track right here, AB. And that's when you're still heating, so there's changes in temperature, so it's a MCAT situation. And the MCAT situation is Q equals M, the mass of the ice is 100 grams. The specific heat capacity of ice is provided in the table, and that's 2.03 joules per gram times degrees Celsius. And the change in temperature along this segment up until 0 is 10 degrees Celsius. I'm just gonna put the 10 degrees Celsius as my final answer. I'm not gonna show the subtraction. All right, so that will give me Q along AB, okay? And that ends up being, let's see, times it by 1,000. So 2030 joules in the end, or 2,030 joules in the end. All right, so now we go to QBC. So I can label it just directly into the equation. So QBC is a phase change. It's fusion. So we're looking at 100 grams. And since we're working in joules, we're going to use 334 joules per gram. QBC ends up being 334 with 2 zeros, so 33,400. Let's go to the next segment. The next segment is Q of CD, and that is not a phase change. That is Q equals MCAT, so 100 grams times it by the specific heat capacity of water. Change in temperature, 100 degrees Celsius. That alone gives you, let's see, 418, adding 4 zeros. Okay, so moving the decimal 4 times over to the right, so 41,840 joules. So QCD. Next segment is QDE. This is a phase change. Phase change means I'm looking at vaporization, delta H vaporization. That's 2,260 joules per gram. And this one gives you a really large number. It's 226,000 QDE. The last segment, this is a long problem for a reason here. The last segment is, I'm going to write it up here, Q of EF, and that is mass, which is 100 grams. That's just heating the object when it's steam, and steam specific heat capacity is 2.01 joules per gram times degrees Celsius. And of course, the change in temperature there is 5 degrees. Calculating QEF, when you're completely done with that, let's see, it's 100 times 2.01 and 5 degrees, and that's just 1,005 joules. Okay, so we have all our segments. I'm going to just circle it. So I have AB, I have BC, I have CD, I have DE. And what we're going to do is we're going to create a curve, a heat curve with that. I'm going to put blue. I'm going to make my... So my first segment is actually from 0 to, or negative 10. So say this is our negative 10 here. And the amount of heat for the first stretch. And what I'm going to do is look at the biggest number. The biggest number is 226,000. So I'm going to say this is 225,000. I'm making nice numbers out of this. So halfway would be 112,000, right? So I'm going to make it a little less, so that's 100,000. 100,000. A little less than halfway. I'm going to hit 50, 150 around here. This allows me to estimate between values. So here's 50,000. Okay. So from AB is this segment. So this is my A. And it's only going to stretch 2,000, which is hardly anywhere right here. And then it's going to go through BC, which is 33,000, which if you add 2,030 to 33,000, you're about a little more than halfway. So I'm going to end my segment a little bit more than halfway right here. So that's where 35,000 is. So this is A, B, C. And then I'm going to go through a stretch of CD. So once again, I'm going to tally everything up. Tally from AB plus this, and that will give me the final wherever that heat ends, okay? So if I take 2,030 plus 33,400 plus 41,840, I will get 77,000. So it's a little bit, 75 is right here in the middle between 50 and 100. So 77 is right here. So gauging, just estimating all the way to 100 degrees right here. So this is my CD segment. DE segment is very long. It's 226,000. So where does that end? Well, I'm going to add that 77,000 to 226,000, and it's pretty big. Oh, I poorly estimated everything, but it's going to go stretch beyond over here to, let's just say this is 303,000. 303,000. Because that's where it approximately, it's 303,270. So this is D. And then the last segment is just 1,000, so it's hardly much of a stretch. It's very short, and so this is F here. Again, you just estimate all those different points that this will hit in the end at those segmented parts. So you can either write that in if you'd like, and I might just write that in as a way to help you see that this is like 2030. This is, and I want to be as precise as possible, 35,430. I'm just adding in as I go, additive values here. 41,000, that's 77,270. And once again, this one is 303,000. 303,270. Okay. So notice how the stretch of vaporization requires a lot of heat. And that stretch, that long stretch, is why boiling, you're trying to overcome from a liquid phase to a gas phase, which really is a significant increase in distance between particles. And to do that requires a lot of kinetic energy, or heat to be absorbed. So, part of thermochemistry involves discussing a lot more than just enthalpy, which is the bond, the potential energy stored in the bonds. A lot of reactions actually depend on something called entropy as well. And entropy measures disorder in the universe. And it's not enough for us to be able to just look at one variable like enthalpy to discuss whether a reaction is spontaneous or not. You have to actually consider entropy. And so there's an equation that kind of sets us up for all of those ideas rolled into one. And this equation involves Gibbs free energy. What does Gibbs free energy describe? It describes whether the reaction that you're looking at is going to occur or not. And really, it's occurring without a continuous source of energy. And if we have a reaction that will occur without having to put continuously energy into it, that means that reaction can help us to do work. And it will give us energy overall. So now enthalpy is one to consider. We have to consider the bond, the heat content in the chemical reaction, really among the bonds in that reaction. Entropy is a measurement of disorder, so we need to be able to understand that nature favors this idea of disorder. We see it in your room all the time. The minute you clean it, it becomes more disorderly. So nature favors a lot of entropy. And that's why one of the laws of thermodynamics says that the entropy of the universe always increases. Now, there's a couple of things to remember. Delta G, if it's a negative value, the change in Gibbs free energy, negative means the reaction is spontaneous. Equal to zero means it's in chemical equilibrium. We'll talk about equilibrium in more detail soon. If the delta G is greater than zero, that means the reaction is non-spontaneous. We all know about enthalpy. Change in enthalpy being negative means it's exothermic, positive, endothermic. The reaction having a positive um, uh, delta S, which is change in disorder, that means there's more disorder. If it's negative, that means it is less disorder. The equation that links all these three variables together is this equation right here. You'll see how to utilize that equation in each of these circumstances. Okay, let's go ahead and look at Gibbs free energy first. How to utilize this equation. So here we're given, it says in equilibrium is this. And so the word equilibrium means that delta G is 0. That's the one thing that I'm always going to point out. What is its boiling point in degrees Celsius if these two values right here are what they are? Now, always take a look at the units. Notice how this is in joules, this is in kilojoules. I'm actually going to make it a point to convert the entropy into kilojoules, okay? So all it is moving it 1, 2, 3 spaces over to the left. So I have a decimal point right there. All right, since G is 0, 0 here, I'm left with this equation equaling 0. So I can rearrange delta S over to this side. Now I have this equation of delta H standard equals T times delta S. So I'm trying to solve for T, the boiling point temperature. So T, all I have to do is substitute 40.65 kilojoules per mole equaling T times delta S, which is 0.109 kilojoules per mole, times Kelvin. Yikes. That means I have to have my temperature. My temperature will be solved for Kelvin. So it has to be in units of Kelvin. That's why I'm always noticing my units. That helps me to know, hey, this is what I'm going to get my value in Kelvin units. So dividing those two values, pretty easy equation to utilize. You get 373 Kelvin, which, subtracting 273 from that, you will get your degrees Celsius, which is 100 degrees Celsius. Guess what temperature water boils? This is water boiling. It's going from a liquid to a gas in equilibrium with one another. And so this is the boiling point temperature. That makes sense. Now let's go to the next question. This question is about why the change in enthalpy for this reaction aligns with the delta H being what it is, which is positive. Well, when you boil, don't you agree that you need to add heat to the liquid to make it a gas? So it's endothermic. So this reaction being positive suggests the reaction is endothermic, or the phase change is endothermic. So I'm going to say phase change. And that endothermic aspect of the reaction is the reason why the or the phase change between liquid water to a gas is going to be an endothermic process because it's called boiling. When I boil, I'm going to have to add heat overall. Okay? All right, now we go to the next one. Now it's going to be an entropy. Would the temperature in the above equation be recorded in Celsius or Kelvin? It is dependent. It's dependent on what the S is. So if the S is in Kelvin here, I would expect the problem to be in Kelvin. But if this was in Celsius, So this value was switched to degrees Celsius, then it would be degrees Celsius. But in this case, it's Kelvin because the units is in Kelvin. So Kelvin is the answer because delta S is in units of joules per mole times, and I'm going to write the Kelvin in red so we can highlight the red, the Kelvin. Okay, how does this equation work? Again, I'm giving you just a very broad idea of how Gibbs free energy and enthalpy and disorder work, okay? So, if this is the equation that links them all together. So, if you have a positive entropy, change in entropy, and a negative change in enthalpy, what you will end up with is this. You have a negative of this term, so this term will be negative. With a negative enthalpy, your value for Gibbs free energy must be negative. And what that negative means is this reaction is going to be spontaneous. So you can use these signs for certain reactions, for most reactions, and be able to predict to some degree whether the reaction will be spontaneous or not. So this here means it's spontaneous. Spontaneous if it's negative, okay? Likewise, let's go over here. If you have positive and negative, it's still going to be spontaneous. No matter what, that positive entropy and negative enthalpy is going to give you a negative Gibbs free energy. Now let's look at the next scenario. In the next scenario, you're looking at a negative entropy and a positive enthalpy. Okay, so positive here, negative here. And it's the same over here, but let's look at how the math works, okay? Now you have a negative of a negative. What's the negative of a negative? Well, it's a positive, right? So you're adding a positive. So the sign of this the sign has to be a positive because then when you add a positive plus a positive gives you a positive. So it must be a positive. The same thing here where the negative of a negative gives you a positive, and so you're adding two positive values, which gives you a positive. Next one, in the next scenario, these are all different scenarios for different types of problems. So here we have positive and positive, both instances, but in this case you're going to add a negative term to that. And so depending on temperature, if the temperature is low, that means there's a very little small, this term becomes a very small term. That means the positive overpowers the negative. That means this is positive. Whereas at high temperature, so this T is high. So this was T low, right? This is T high. That means the term that multiplies with the enthalpy or change in disorder, which is entropy, is going to be a large term. So that's a large negative term. That large negative term will overpower this positive term, giving us a negative value. So in this case, where both entropy and enthalpy are positive, this will vary depending on the temperature. Likewise, let's look at the next scenario. Here we have negative and negative, and negative and negative. But we know what negative is. We know that negative means it's adding a positive value here. So depending on the T value, if the T is high or low, so if T is low in this instance, you're looking at a term, the positive term, that is going to be low, so the negative overpowers the positive term, and that's why it's negative in the end. Over here, high value for T gives you a greater term here, and so the greater positive term is going to overpower the negative. Okay, and thus delta G is going to be positive. So these are all conceptual explanations of how this works. Okay. All right, let's go to the number 1 and 2. In number 1 and 2, number 1 is asking, does the entropy of the system increase or decrease for the following changes? And if it's increasing, that means it's going to be the change in system of the or the change in entropy is going to be positive versus negative. All right, water boiling. What's happening when water boils? Well, when water boils, we know that water is going from a liquid phase in equilibrium to the water as a gas phase. And that absorbs energy, so there's heat on the reactant side. Now, notice the state of matter. Is it getting more disorder or less disorder? Well, if you're going from a liquid state to a gas states have much more disorder than liquid states. So it looks like the entropy is increasing. And I'll write it. Delta S is getting positive. So this is a positive value. Keep on going. Let's look at B. In B, it's important to look at the states of matter, basically, when you're looking at this. So in B, you're looking at a solid becoming a solid and a gas. So it's becoming more disorder. Not only are there more particles, there's 2 moles of particles versus 1 mole on the reactant side, you're actually becoming, there's a gas that's forming. And that gas has a lot more entropy disorder than the solids that are paired with it. So the entropy is increasing also here, so it's positive. In this last instance, you're going from 4 moles of gases. Look, there's 1 here, there's 3 here, so there's 4 moles of gases becomes 2 moles of gases here. So actually the entropy is decreasing, so there's less disorder, so it's 0. Or a negative value, so this is a negative value. Right, let's work to the last. In the last, what we're going to do is we're going to predict the sign of the standard Gibbs free energy, justifying your answer as we go, okay? So we're looking at if sign meaning positive or negative. So whenever I hear the word sign, I'm looking at positive, negative, or no change, 0 change. All right, let's go to the first one. In the first one, we're seeing that your reaction is going from a solid to 2 moles of gases. So it looks like the entropy, if we're speaking of entropy, is going to be positive in the end. You're also decomposing. This is a decomposition reaction. In a decomposition reaction, you're going to need heat on the reactant side. So this is an endothermic reaction. So if G is positive, or sorry, if delta H is positive, and so I'm going to write the reaction. It's always good to see how this all relates to this reaction. If you have a positive delta H, positive delta S, that means that it depends on the temperature here. So G could be positive depending on if the temperature is high or low. If the temperature is high, that means the G is negative. If the temperature is low, then G is positive. So I'm going to say varies. If it varies, that means it depends on the temperature. So I really can't tell. If it's high temperature versus low temperature, we can tell. We can say that G is going to be, if it's high temp, that means G is going to be a negative value, so less than 0, that means it's spontaneous. If low temperature, that means G is going to be greater than 0, which means it's going to be non-spontaneous. That means the reaction will depend on the temperature significantly. Again, just look at this variable and see how these plugged into here, just like we did earlier in the practice in the previous page, would change the G value in the end. These have values. If it has values, you're going to calculate the G. There's more quantitativeness, or it's more quantitative when you can do that. So when I'm gonna do B on the bottom here, since I can calculate it. I can predict the sign too, but I'm going to calculate it just to be more quantitative. So I'm going to do delta G equals, and negative 273 kilojoules per mole minus temperature I don't know the temperature, so I'm just going to still put T in there unless it tells you temperature. Oh, we do know the temperature. It's 25 degrees Celsius. So I'm going to put it in Kelvin, which is 298 Kelvin. And then I'm going to multiply that times the delta S, which is by the way, 0.326. And that's in kilojoules per mole times Kelvin. And doing the math and everything, I get, by the way, a negative of a negative is a positive, so I kind of like turning that into the positive that it needs to be. And adding your values together, I get negative 475 kilojoules per mole. Now that negative value for delta G means the reaction is in fact spontaneous. So you can see from just the value whether the reaction is spontaneous or not. Once again, spontaneity is the idea that the reaction will occur without a continuous source of energy. Okay, I'm going to say 475 negative, and it is spontaneous in the chart. All right, going on to C, I can see that this reaction is a combustion reaction. Combustion reactions are very exothermic. And look at the moles of gases. A mole of liquid, 8 moles of gases, forms 11 moles of gases, which means the reaction is getting more disorderly, and it's exothermic. Again, negative value here, positive value here, and there's a subtraction going on right here. So it's a negative and a negative added together gives you definitely a negative. There's no doubt about it, which means this reaction is spontaneous. Calculating for D. In D, delta G equals 58.0 kilojoules per mole. And then I'm going to subtract 298 Kelvin times 0.77 kilojoules per mole times Kelvin. And when I do my math, I get, in the end, positive 5.3 kilojoules. And that positive 5.3 kilojoules, it's a positive value, means the reaction is non-spontaneous. So there's a quantitative way to tell whether a reaction is going to occur or not using this thermodynamic situation where we're looking at enthalpy, entropy, and Gibbs free energy. This ends the unit.